This question begins by asking us to write an equation for the reaction of this compound, methyl benzoate, with nitric acid. So nitration, remember, puts an NO2 group onto the ring in place of a hydrogen. So the decision you have to make is where it goes, and it tells you that the ester group here is electron withdrawing, and what you have to remember is that that will direct substitution to the 3 position. It also deactivates the ring, as does the nitro group that you put onto it, so it's likely only to substitute once. So although it's possible it could go to both 3 and 5, it's likely only to go on once, and therefore it's easier just to stick to just a single substitution. Okay, so it's going to substitute once at that position, so that will give you ester group unchanged, but now an NO2 group. Must connect up to the N because that's the atom that's connected at that position, and because it asks for an equation, it's got to balance. Organic chemistry equations have to balance just like every other one, and obviously you can work it out if necessary, but it's easier when you're learning your reactions to include learning the equations and therefore realise that it produces H2O as the other product. Now what it then asks you to do is to compare the rate of this reaction with the rate of nitration of benzene under the same conditions. So again, this is about the effect of having an electron withdrawing group there. So what you need to say is that the electron withdrawing group decreases the pi electron density in the ring. Okay, it's pulling electrons that way, so it decreases the electron density in the ring, and that makes it less attractive to an electrophile. Remember, the mechanism for this reaction involves NO2 plus needing to be attracted to the pi electrons in the ring, and the lower the electron density there, the weaker that attraction will be, and the slower that will make the reaction. So the answer is that benzene will react faster because it doesn't have an electron withdrawing group, and therefore it has a higher pi electron density in the ring, which makes it more attractive to an electrophile. Okay, now we have a couple of questions about using gas chromatography to analyse what's going on in the reaction. And first of all, it asks us why methyl benzoate might have a different retention time in gas chromatography from the nitromethyl benzoate that's formed. It's not asking you to be specific about whether you would expect it to be a shorter or longer retention time and exactly what kind of interactions would be involved in determining that, because you can't do that simply because it doesn't tell you anything about the stationary phase that's being used in the gas chromatography. So don't try to get bogged down in too much detail. It's really just wanting you to say in general terms that the nitration of the compound is likely to change its solubility in the stationary phase. Remember, in gas chromatography you have this liquid lining the column, and it's when a substance dissolves in it that its progress through the column gets slowed down. So if you change the solubility, you change the retention time. More specifically than that, though, you need to say that the more soluble the compound is, the longer the retention time will be. Okay, because obviously more solubility means more time spent not moving because you're trapped in the stationary phase. So you need to spell out that methyl benzoate and the product are likely to have different solubilities in a stationary phase, and whichever one has the greater solubility will have the longer retention time. The next thing says, well, okay, if we have a working gas chromatography system, how could we use it to obtain those quantitative data? In other words, to measure how much product had been formed as a function of time. And the answer to that is, remember that in a gas chromatogram you get a series of peaks, so it might look something like this, and it's the area under a peak. So if we draw a baseline across there, it's this peak area that is proportional to the amount of that substance that's been injected, and therefore if you inject a fixed volume to the concentration of the substance in the solution. So you need to talk about the idea of, first of all, measuring the area of the peak in the chromatogram. But all you know from that is that it's proportional to the concentration. If you want to actually get numbers, what you need to do is to calibrate your GC system. So that's important. So calibration is a very important idea. And you need to say briefly what that means, which is that you inject a series of samples of known concentration into the chromatograph and plot a graph of peak area against concentration for those samples, so that you can then read off from that, by measuring the peak area in your thing, what its concentration must have been. Okay, so don't just say calibrate it, you've got to say a bit more than that. So calibration means injecting a series of samples of known concentration into your column, measuring the peak areas that they give, and plotting a calibration graph of peak area against concentration, because you can then use that to relate the peak area in your experiment to what the concentration must have been. The next little bit is asking about the kinetic analysis. So in this experiment we've got two reactants and we've got a catalyst, which is the conch sulfuric acid. And yet what we're trying to do in the kinetic analysis is to keep it very simple and just to focus on the methyl benzoate, and it's saying, well, how can we get away with that? So for the nitric acid, the answer has to do with its concentration, because it tells us that the concentration of the nitric acid is really very high, much higher than the methyl benzoate, so that when most or all of the methyl benzoate has been used up, the concentration of this has, in percentage terms, hardly changed. And that's the idea. So it's not enough just to say, oh, it's because it's at a very high concentration. It's because it's at a very high concentration relative to the other reactant, or if you like, it's in huge excess relative to the other reactant, and therefore its concentration hardly changes during the reaction. For the sulfuric acid, it's different. The point about the sulfuric acid is that it's a catalyst, and therefore by definition it's not used up during the reaction, so it's perfectly reasonable to assume that its concentration stays constant. Part F asks us to determine the order of reaction with respect to methyl benzoate. So when you get a graph like this of concentration against time, and you're asked a question like this, you should think of using the half-life method. Okay, so what we can do is to use this graph to plot successive half-lives. Now on the graph there, you actually didn't have the curve drawn, you had to draw that yourself, but it was very clear from the distribution of points that you could draw a smooth curve through it, and you could then use that to find successive half-lives. So just to remind you how to do that, it's the starting concentration is 1.0 moles per dm cubed, or actually is it, what is it? Oh, sorry, grams per dm cubed, yes, so 1.0 grams per dm cubed. So the first half-life is the time it takes to drop to half of that. So if this is 0.5 grams per dm cubed, we just draw a line across there till it hits the curve, drop a vertical down, and say, right, that is the first half-life, which we call T half number 1. And then we say, right, how long does it take to halve again? In other words, to drop to 0.25. So we draw a second line across, again drop it down, and that's our second half-life, which we can write as T half number 2. And you just then need to make sure that you recorded the values of those, and you should find that they're both around 2.5 minutes. They probably won't come out to be exactly the same, because obviously, particularly as it was a hand-drawn curve, there's going to be a significant margin for error. but they should both be in the region of about 2.5 minutes each. And so the way you answer the question is to say that successive half-lives are constant. In other words, that's the first one, that's the second one that follows it, and they are the same. So successive half-lives are constant, and that means that it's first order with respect to methyl benzoate. Okay, then it asks us to use the data to find the value of the rate constant. Because remember, we've got a rate equation then, having established that's first order. Rate is equal to K times methyl benzoate. And because this is a special case where it's just a first order reaction, we have this special trick that we can use, which is that K is equal to the natural log of 2 divided by the half-life, and obviously the half-life is constant, so there is just one value for that. You can only do that for first order reactions. But it's very quick and easy, so that's equal to log of 2 over 2.5, because the half-life was 2.5 minutes, which is 0.28, and it's going to have a unit. Remember, the recipe for units of K is that if X is the overall order of reaction, which is the sum of the individual orders. Now here it's very simple because there is only one concentration involved and it's first order, so X is equal to 1. But normally it would be the sum of the individual orders. So if X is the overall order, the units of K are moles to the 1 minus X, dm to the 3x minus 3, seconds to the minus 1, or in this case, because we're working in minutes, that will be minutes to the minus 1. You have to be careful about that. It's most commonly seconds, but it can be whatever time unit you've got. So here, minutes to the minus 1. So X is 1, so moles to the 0, dm to the 3 1's the 3 minus 3 is 0, so these terms vanish, and it's just minutes to the minus 1 is the unit, and that's the answer. There was an alternative strategy. You could have drawn a tangent to the curve. For example, you could have drawn an initial tangent at the beginning, something like that, measured its gradient, so the vertical change divided by the horizontal change, in order to get the rate, and then just rearrange this equation to solve for K. It's a lot more long-winded, but it should give you a vaguely similar number, and you would get full marks for that. But try to remember this, because when you do have a first order reaction, it's much quicker. Part H is asking us to draw a Boltzmann distribution and use it to explain how a catalyst can increase the rate of reaction. So this is one of those set piece things. You need to be absolutely certain you can do stuff like this, because there was no puzzling stuff out involved here. It was simply a case of knowing how to do this. So the first thing is you need to be able to draw a Boltzmann distribution. So the key feature is that it has to start at the origin, rises up to a peak, and then comes down more gradually on that side. So you want to make it look distinctly asymmetrical like that. A whale-back shape is how it's sometimes described. And you want to make sure that it doesn't hit the axis again down here, because it's actually asymptotic, which means it gets closer and closer but never in principle actually reaches it. So that needs to be clear that it doesn't quite hit the axis down there. So that's the general shape. You then need to remember what the axes are. So this along the bottom is energy, or kinetic energy it's sometimes written as, but it's just the energy of the particles. And this is the number of particles on that axis. So that's the general shape of the distribution, and then onto that you can mark the activation energy. And the activation energy is just a vertical line because it corresponds to a particular value of the energy. So that's the activation energy. And the important issue, remember, is that area. So the area of the graph in the part where the energy is above the activation energy, that represents the population of molecules with enough energy to react when they collide. And what the catalyst does is to provide an alternative pathway with a lower activation energy. So you mark on a second activation energy and you say this is the activation energy with a catalyst. And of course, by lowering the activation energy, you increase the population of molecules with enough energy to react when they collide. So kind of diagram of that showing that it's about the areas is quite an effective way of doing that. So that's what you need to have on the diagram. In terms of what you need to write to go along with it, the first thing I think is the statement that you always make about the general way catalysts work, which is that they provide an alternative reaction pathway which has a lower activation energy. So you need to make that statement, and then you need to relate that to this diagram and say why it works. And you say, therefore, as the diagram shows, there will be a bigger population of molecules with enough energy to react when they collide, and therefore successful collisions will happen more frequently, hence the rate increases. That statement is quite important that you get it right. It's not just that more successful collisions occur, because in the end, the reaction will go to completion. It will just take longer if the activation energy is higher. So it's not that more successful collisions occur, it's that they occur more often, more frequently, and therefore that the rate increases. So make sure you get all the marks, get the diagram right, get the statement about an alternative pathway with a lower activation energy, and then this point that because there's a bigger population with enough energy to react when they collide, successful collisions will happen more often, and therefore the rate will increase.